we do need to learn a little bit of physics to understand this. So light, I mean, we all know what light is, right? It's light in the room right now. We turned on the lights. But wait, what is light? Ever thought about that? What is it? It's electromagnetic radiation. And don't be afraid of that word radiation. So electromagnetic radiation is composed of perpendicular oscillating waves. One is an electric field and one is a magnetic field. An electric field is a region where an electrically charged particle is going to experience a force. Magnetic field is a region where a magnetized particle experiences a force. All electromagnetic waves move through space at the same speed, and that speed is constant, and it's called the speed of light. So the speed of light is 3.00 times 10 to the 8th meters per second. You do not need to memorize that. You don't need to memorize this one either. But just to give you an idea how fast that is, 186,000 miles per second. 186,000. That's fast enough to circle the Earth 7 times in 1 second. That's like really, really fast, right? That's how fast light travels. So here's an illustration of what we mean by those oscillating waves. So here's the electric field component is oscillating up and down in this plane as it's traveling over, and the magnetic field is at 90 degrees and is traveling in the same direction. If that doesn't make any sense, that's okay. So we all saw and heard some of this recently, didn't we? The atmospheric river brought it. It's not even done with us, bringing all kinds of stuff to California. So here we have a picture of lightning striking something over here in the distance. And we see the lightning strike, and then we hear the thunder later. But they happened at the same time. Light travels much faster, 3 times 10 to the 8th meters per second. Sound is slower. It travels at 340 meters per second. So you can see the lightning strike, and then depending on how far away you are, there's going to be a delay when you hear that thunder. And that's where well, if you count the number of seconds between them, that's related to the number of miles away, right? Any questions about that? So waves have some characteristics. So one of those is called the amplitude. That's how tall the wave is. And so the wave oscillates. It goes up and down and up and down. And it goes through this, well, I guess you could say goes through zero, where it's going above zero and then an equal amount below zero. And so the amplitude is from this center line to the peak of a wave, or from the center line to the trough of a wave. It's going to be the same. So the amplitude measures how intense the light is, how bright it is. The larger the amplitude, the brighter the light. The other thing we can measure is the wavelength, the distance from one peak to another peak. That's called the wavelength. It's the length of the wave. The wavelength, different wavelengths, our bodies perceive as different colors. So here, if we have light with a long wavelength, we may see that as red, whereas light with a shorter wavelength will appear blue to us. And in the middle are colors like yellow. So the difference between these colors is the wavelength of the electromagnetic radiation. The amplitude, how tall that wave is the brightness. So you could have bright red light or dim red light. Bright yellow, dim yellow. But they would have the same wavelengths. They just have different amplitudes. Any questions? So we talked about amplitude and wavelength, and then there's another concept called frequency. So frequency is the number of waves that pass a point in a given period of time, sometimes referred to as the number of cycles. So the wave going up and going down and coming back to the middle would be one cycle. So the units for frequency are hertz, and the abbreviation is capital HZ, and hertz means cycles per second or per second, whatever's per second. Okay? So the total energy of a wave is proportional to its amplitude and to its frequency. The larger the amplitude, the more energy, the more force it has. The more frequently the waves strike, the more force it has, the more energy there is. So if we imagine ourselves at the beach, you're standing at the beach, woohoo, we're at the beach. And you think about the waves rolling in. And we've got just some gentle waves coming in, and you're standing out there, like knee deep in the water, and the waves are hitting you. It's like, oh, this is nice, right? So, assuming that these waves are traveling at the same speed, so here you might, count 1 wave, 2 waves, 3 waves. So maybe you get, 30 waves in a minute, right? What if the waves were a lot bigger? Now, this is probably going to knock you over, right? A really big wave. Or what if they're a lot more frequent? Instead of wave, it's wave, 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 wave. It's going to hit you more, right? Does that make sense? More frequent, more energy. Bigger, taller, more energy. For waves that travel at the same speed, which is true of electromagnetic radiation, it all moves at the same speed, the speed of light. A shorter wavelength means a higher frequency. So the wavelength and the frequency of electromagnetic radiation is inversely proportional. If the wavelength is long, the frequency is short. So the speed of light is constant, and so we can have this equation here where the frequency is equal to the speed of light divided by the wavelength. So if we know the wavelength, we can find the frequency. If we know the frequency, we can find the wavelength. Now, this letter here, it looks like a V. This is a V. That's a nu. It's a Greek letter. That's not confusing at all. I didn't make this up. We just have to live with it. So you kind of have to watch out for that, because if you think that's a V for like velocity, then it's going to mislead you in calculating things, right? Like the first homework problem. So color. The color of light is determined by its wavelength, which is related to its frequency, right? So what we perceive as white light is actually a mixture of all the different colors, all the different wavelengths in the spectrum. And in that spectrum, we have these colors: red, orange, yellow, green, blue, indigo, and violet. I don't know about you, but in the last week or so, I've seen a couple of rather spectacular rainbows, right? And the colors in the rainbow are always in the same order, right? That's why when you look at a drawing that a child makes of a rainbow, you're like, well, that's really pretty, but I don't know, there's something not quite right about it. Because they don't pay attention to the order of the colors, right? And they may have the yellow next to the blue, right? And it doesn't happen in a real rainbow. This is the order that the colors are in the rainbow. And we should remember that. And what I've always used is Roy G. Biv. So, kind of a weird name, right? His first name's Roy, middle initial G, last name Biv. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Okay? So, our perception of color is kind of interesting. When we see something as being red, like the shirt that this woman's wearing, we see that as red. That's because as the white light hits her sweater or shirt, it's absorbing some of the colors and reflecting other colors. A red shirt is reflecting red light and absorbing other colors. And so we see the reflected red light. Right? So the observed color is mostly what's being reflected as opposed to what's being absorbed. So something that's black is absorbing most of the light. This is why, like, if you have a black lab or a cat that's all black, they're beautiful creatures. It's so hard to get a good photograph of them, right? Because they just suck up all the light. And they just kind of look like this black blob. And you're like, but that's not how they look in real life. It's because they're just absorbing all the light. So there's some calculations we need to be able to do. Here's an example. A laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. So we're going to highlight numbers that are given, and we're going to highlight what we're supposed to find. So we're told that the wavelength is 515 nanometers. The symbol for wavelength is the Greek letter lambda, which is a lot like an upside down lowercase y, lambda. They're asking us to calculate the frequency. The letter for frequency is that thing that looks like a V, nu. And so we just saw an equation where the frequency is equal to the speed of light, represented by the letter c, divided by lambda, the wavelength. It's an equation. And the speed of light, we can look that up, and that is 3.00 times 10 to the 8th meters per second. So this is an equation that allows me to calculate frequency, right? So I want the speed of light in the numerator, 3.00 times 10 to the 8th meters per second, and I'm dividing by the wavelength, 515 nanometers. Are the meters and nanometers going to cancel out? No, they're not. The fast way to fix that is to remember, well, nano represents times 10 to the minus 9. That's the meaning of nano. So what I'm going to do here, instead of writing the n, I'm going to write what it means. Times 10 to the minus 9 meters. And then the meters are going to cancel out, and the unit I'm left with is 1 over seconds. So I've got 3 EE8 divided by 515 EE negative 9. And I should have 3 sig figs here, so I'm just going to go ahead and round it. 5.83 times 10 to the 14. On your calculator, mine's showing 5.8252427118 E14. That E14 is like super important, because that's times 10 to the 14th. So always look at the end of the number, make sure you're including everything. So that could also be called 5.83 times 10 to the 14th hertz. Any questions? Oh, I guess this is something worth pointing out. You see up here? So 1 over s is the same as s to the negative 1 power. And both of those are equal to hertz, Hz. I don't care how you express it, but you need to be comfortable with seeing it in all these different ways. Okay, so visible light is part of the electromagnetic spectrum. That's the light we can see, the different colors in Roy G. Biv. But there's part of the spectrum has shorter wavelengths. Shorter wavelength means higher frequency. And so higher frequency, that's the waves banging on you more frequently, right? Is that more energy or less? That's more energy. More frequently being hit is higher energy. So high frequency has higher energy. That's shorter. So gamma rays have the highest energy. They have the shortest wavelength. At the other end are radio waves. Those have very long wavelengths, very low frequencies, and those have the lowest energy. So the signal that your radio is picking up is the same kind of a thing as the light that we see. It's just, it has a different frequency. It travels at the same speed. So the radiation that has high energy is dangerous to living organisms because it can damage the tissue. It has enough energy that it can actually ionize the molecules in your body. So if the molecules turn into ions, then they're not going to react chemically the same as they did before, right? And so obviously that's going to cause some problems. So it's that high energy radiation that gives radiation a bad name. You know, we think about radiation, oh, that's bad, right? Well, some of it's bad, and some of it's really good. So this is the electromagnetic spectrum. This is the same figure that's in your textbook. And I just want to give you a tour of this because it can be a little confusing. So up here we have a frequency scale in hertz. So from 10 to the 4th hertz going up to 10 to the 24 hertz. Here we have a scale indicating the wavelength in meters. So that goes from 10 to the 5th meters to 10 to the minus 15. So on this one, as we're going to the right, the frequency is getting larger. The wavelength is getting smaller. This end is high energy. High frequency, those waves, bang, 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 more energy, right? So this end is high energy, this end is low energy. This part in the middle with the colors, I mean, it's literally jumping out at you, right? And it's got colors and the rest of it's all black and white. And it's like, grab your attention, right? It's important to recognize that all of this came from this little tiny place in the middle. It's expanded here because this is a part of the spectrum that we are interested in because we can see it, right? And if we tried to show you the scale in there, it'd be too small to read. So it's expanded out here, and this is showing us the wavelengths of the different colors. So violet is around 400 nanometers, red is, the 750s. Okay, but that does not mean that red light belongs over here with radio waves. Okay, it's from here. Here we have the names of the different portions of the electromagnetic spectrum. So visible light is a tiny part in the middle, and to higher energy is ultraviolet. So we look at the colors here, red, orange, yellow, green, blue, indigo, violet. Beyond violet is ultraviolet, right? You know, it's bigger, more than violet. Ultraviolet. What does ultraviolet light do? Gives you a sunburn, right? Does that have more energy than like yellow light? Yeah, yellow light won't give you a sunburn, but ultraviolet light will give you a sunburn. So that's another way to remember that this end is more energetic. So we have ultraviolet, and then there's X-rays and gamma rays. Now, X-rays, too much of them is going to be bad for you, but a little bit of X-rays is not going to hurt you, right? Because, you know, you got a broken leg, they're going to do an X-ray so they can see what's wrong and how to help you. But you wouldn't want to be getting X-rays every day, right? Because too much of anything is bad. So X-rays are somewhat dangerous. Gamma rays are much higher in energy, and they are a lot more dangerous. So on the other end, from red, we have infrared, which is below red. So this is you go to a motel and they have got that heat lamp in the bathroom, right? And you turn it on and it's like there's a little bit of visible light there, but mostly it's just giving off heat. That's infrared light. Okay, so it feels warm, but the energy is actually lower than, say, ultraviolet light. You're not going to get a sunburn from the infrared light. So this is lower in energy. And then there's microwaves and radio waves. And microwaves, maybe it doesn't make sense that those are in there because microwaves heat your food up, right? Make things really hot. How can that be lower in energy? Microwaves work to heat your food because they are at a frequency that water can absorb. So microwaves interacting with water cause the water molecules to vibrate more, which increases their kinetic energy, which increases the temperature. So it's the water in your food that is interacting with the microwaves in your microwave oven. And if you try to microwave something that doesn't have any moisture in it, it's not going to go very well. Okay? So I am not going to read the textbook to you about these different portions of light. I'm expecting you to read those for yourself. Okay? Let's talk about them real briefly there. Okay, so a continuous spectrum. So here we have some white light coming into this prism. And the prism separates the light into these different colors. That light doesn't look like it has different colors in it, does it? But this actually has all the colors. The prism can separate that into a spectrum. This is a continuous spectrum, meaning that all the colors are here. There's no gaps in this. So it gives us a rainbow. So this is a use of infrared light. When my daughter was in elementary school, she got to go on a field trip to NASA's Jet Propulsion Lab down in LA. And so of all the zillions of pictures we took there, this was the one I could use in my class. Right? She's 18 now. She'd probably be embarrassed. So this is what we looked like in visible light. And this is what we look like using infrared camera. So the infrared camera, we can't see infrared light, but you can develop sensors that detect infrared light, and that's what the night vision goggles and sorts of things are doing. They're interpreting the infrared radiation. So you see here that where our skin is exposed, you see more of an orange color, right? And see, my phone was pretty hot because I've been taking so many pictures, and apparently my nose was cold. And then, the rest of our bodies are cooler, and then the background behind us is much cooler. And so it's just taking the infrared radiation. It's basically looking at the heat. And so this is really useful for finding living things in the dark. Because like you go out in the forest, somebody's lost in the woods, and you use an infrared camera and you can see, oh, there's a hot spot right there. Well, that, could be a bear, could be a person, right? But you can find them that way. High energy radiation is dangerous, but it can also be beneficial. So there's a procedure called a gamma knife that can be used to get rid of tumors. So, if you've got a tumor in your brain, just going in and cutting it out is probably not going to work most of the time, because you have to cut through brain tissue to get there, right? And you kind of need your brain tissue. So what do you do then? Well, they can use radiation. So this is how they do it. What they do is they take radiation, a gamma ray beam, and they shine it on the tumor, but they come from lots of different directions. So they're going to be it's going to move all over, and these little beams, when the beam goes through the healthy tissue, this one beam only does a little tiny bit of damage. And this beam only does a little tiny bit of damage. So it is damaging the healthy tissue, but only a little tiny bit. But the tumor is the focus of all of those beams, and so the tumor gets it bad, right? So this is a way that they call it gamma knife, because you can kind of cut out a tumor without actually going in with a knife. So there's lots of really cool applications in medicine. Okay, so another thing we need to know about waves is they can interfere with each other. They interact. So if we have two waves that are in phase, meaning their peaks are lined up and their troughs are lined up, when those meet each other, they will have constructive interference, and you'll see an increase in amplitude. The waves are going to get taller. The frequency, the wavelength stays the same, but they're going to get taller. You can also have destructive interference. Here the waves are out of phase. The peak of this one lines up with the trough of that one. If they're perfectly out of phase, they're going to cancel each other out. And this is how noise-canceling headphones work. They take the sound from around you and delay it just a smidge so that it is exactly off peak of the sound is still coming into your ear, and then they broadcast that into your ear, and the two now are out of phase and they cancel each other out. Very cool. You can also experience things like this, jumping on a trampoline with another person. If you jump just right, you're like really getting shot way up there, right? Because the two of you are reinforcing the waves. But you can also have it happen where you were expecting to bounce way up, and you just like, oh, and you like stopped. You're like, how does that happen? Because your wave and the other person's wave were destructively interfering, and you got no bounce. Waves can also diffract. So diffraction is what happens when a traveling wave encounters an obstacle or an opening in a barrier that's about the same size as a wavelength. The waves then bend around it. Traveling particles don't do this, but waves do. So the diffraction of light through two slits separated by a distance comparable to the wavelength will result in an interference pattern, and that is characteristic of all light waves. So here are the waves. These are the crests. So it's going up and down and up and down and up and down and up and down. We're looking from the top. And it's coming through and hitting this hole. What happens is part of this wave goes through the slit, and as it does that, it bends as it comes out. That's what waves do. Can't explain it any better than that because I took physics a really long time ago. But that's what waves do. This is what particles do. Think of, baseballs being thrown at a wall or something, and you hit an opening, the baseball goes straight through. Does going through the door cause it to bend off in another direction? No, not if it didn't hit anything. It's just going to go straight through. If the balls hit the wall, they're going to stop or bounce back, right? So this is what particles do. Waves do not behave like particles. And you can see this using waves in water. They behave the same way. So the interference from two slits. So here we've got a light source. And so this is sending out waves, and they're radiating out in a circle, right? Oops. So the wave is going to hit this slit, and the wave's going to hit this slit. They're going to hit at the same time. And when they hit that slit, then they diffract and they bend, right? So now it kind of looks like we have two new sources of waves because they're bending out from these slits. As these waves continue, they're going to interact with each other. And in some places, they're going to have destructive interference where they're out of phase and they will cancel each other out. And you will see a dark spot like this. Other places, the waves will be in phase and you'll see a bright spot, an increase in the amplitude, like this. This is one of my favorite videos.
Building your online business? Go to Wix.com and set up your...
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today, Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances, besides the fringes of colors on each side of the shadow. The shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
You can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom?
Well, the obvious thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines.
I
Yeah, I think it'll be one line instead of two.
can expect the whole box lit up.
That'd probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No,
I see dots.
How many?
it's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
Kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
2 slits.
2 slits. That's incredible.
Well, all we're doing is we're putting a light through 2 very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved now. The average person's not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
This is basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the
And
same
then they go
pattern.
and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, and then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah,
That's
that's
because
working.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So,
between
there's,
red
so
and blue.
that red bit over there, the green part is just, I'm seeing
It's a
that,
different-
it's just different
different
wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Hey, thank you.
I have been enlightened. Literally.
Any questions? Could you see the stripes in the water there?
I really like that video. And that's the guy with the hat.
So light behaves like a wave. So that's what he was doing here with those 2 balls on the water. He's making these waves, and as they come out, right, they're going to interfere with each other at different points. So light behaves as a wave. Light also behaves as a particle. So it was observed that many metals will emit electrons if you shine a light on their surface. It's called the photoelectric effect. And classic wave theory, Newtonian physics, attributed this to the effect of the light energy being transferred to the electrons. According to that theory, only the intensity of the light, the amplitude, should matter. And that predicts that if you use a dim light, there would be a lag time. You'd have to wait for the electrons to absorb enough energy before they could be emitted and ejected. So this is a photoelectric effect device. So here we have, this is an evacuated chamber. We've got a piece of metal here. and an electrode over here. So this is got a positive voltage on it, and this has a negative voltage on it. But there's this big gap. So no electric current is going to flow because there's no connection. But if an electron leaves the metal, it's negatively charged, and it's going to be attracted to this positive terminal. So it will go through the air to the positive terminal, and we can measure that using this current meter. So light is hitting the surface, causing electrons to be ejected, and we can measure those. So what we find is that the rate of electron ejection changes with the frequency of the light. So as you start from low frequency and increase the frequency, you've got nothing happening. And you get to this point, which is the threshold frequency, and all of a sudden you get a whole bunch of electrons being emitted. The difference between bright light and dim light is that you're going to get a bigger signal here from the bright light than from the low light. But both of them are going to start at the same frequency. There is no lag time. The previous theory said, well, if you're down here, you just have to wait a while for the electrons to absorb enough energy. This is saying, no, that doesn't work at all. So Einstein's explanation for this is that the light energy is being delivered to the electrons in packets or particles of energy. A packet of light is called a photon or a quantum. So the energy of the photon, this is where I finally define these letters, the energy of the photon is directly proportional to its frequency. That's a funny Greek letter, nu. It's inversely proportional to the wavelength, symbolized by lambda. The proportionality constant is called Planck's constant and has this value 6.626 times 10 to the minus 34 joule seconds. We'll be using that, but you don't need to memorize that. So the energy of light is equal to a constant times its frequency, or a constant times the speed of light over the wavelength. So if the wavelength is longer, the energy is lower. If the frequency is higher, the energy is higher. We can calculate the energy. A 100 watt light bulb radiates energy at a rate of 100 joules per second. And they're explaining here that the watt is a unit of power. Power is energy over time. And that's defined as 1 joule per second. So 100 watts is 100 joules per second. If all of the light that's emitted has a wavelength of 525 nanometers, how many photons are emitted in 1 second? Assume 3 sig figs in the calculation. Okay, this is a critical thinking type problem, and we can use units to help us figure this out. So 100 watts is the same as 100 joules per second, but watts is what we're familiar with in terms of how much energy a light bulb's using, right? So we're not actually going to use that one, we're going to use this one. And then here we have a wavelength. So we have 100 joules per second, and we have 525 nanometers. So that's the wavelength of the light. Joule is a unit of energy, right? It's the energy per second. Can we calculate the energy of the light? Oh, how about this one right here? The energy of light is equal to Planck's constant, that guy, times the speed of light over the wavelength. 6.626 times 10 to the minus 34. as units of joule times seconds. The speed of light is 3.00 times 10 to the 8th meters per second. So we've got that equation. The energy of the light is equal to hc over lambda. That's the energy of one photon of the light, one piece of it. So that's 6.626 times 10 to the negative 34 joules times second times 3.00 times 10 to the 8th meters per second divided by the wavelength. Now, again, we've got meters up here, and our wavelength is in nanometers. So instead of writing the prefix n, I'm going to write what it means, times 10 to the minus 9, and that's meters. So if I check out my units, the seconds cancel, and the meters cancel, and I'm going to end up with joules. So the energy will be 3.7863 times 10 to the minus 19 joules. That is equal to the energy of one photon. I've got 100 joules per second, and it's asking how many photons would be emitted in 1 second. So I can start my path with 1 second, and I can convert that to the number of joules, and then I can convert that to number of photons. This is a conversion factor between joules and seconds, and this is between joules and numbers of photons. So I've got 1 second times 100 joules for every second, and I'm getting 1 photon for every 3.7863 times 10 to the minus 19 joules. So my seconds cancel and my joules cancel. And so the calculator tells me 2.64 times 10 to the 20th photons. A 100 watt light bulb is giving off 2.64 times 10 to the 20th photons every second. Does it make sense that it's a really big number? Because a photon is like really, really small, right? It's a piece of light. I mean, it's hard to think about a piece of light. Any questions? So this is something you should be able to do for an exam, and I'm going to show you how you can remember it. So this is asking us to arrange 3 colors of visible light, red, green, and blue, in order of increasing wavelength, frequency, and energy. I can almost guarantee you there'll be a question like this on the next exam. Okay, so this is what I'm going to think about. I'm going to think about Roy G. Biv. Roy G. Biv. So there's my red, orange, yellow, green, blue, indigo, violet. And what kind of energy is past violet? Ultraviolet. Is ultraviolet have more energy or less energy than regular light? More, because it can give you a sunburn, right? Some of us are much more aware of that than others. But so this is more energy on this end, right? Less energy on this end. If we think about waves, we can look at this and see, we can compare the wavelengths, right? That's the wavelength from the top of one to the top of the next one, and here's the wavelength for that one. This one is a longer wavelength, right? It's longer here. So this is longer wavelength, and this is shorter wavelength. How does the frequency of these compare? Which one, think of yourself at the beach, and the waves are coming. All of this stuff moves at the same speed. So we have these moving at the same speed towards the person on the beach. Which one's more frequent? The top one or the bottom one? The bottom one. So the bottom one, this is higher frequency, and this is lower frequency. Make sense? Which one of these is higher energy? The one on the bottom. It looks more energetic to me, right? This one this one right? So this is the high energy one. So higher energy. And this one's lower energy. Oops, did not mean to do that. Lower energy. That makes sense, right? So then if we go to our colors here, Roy G. Biv, and we decided that this is more energy is the larger frequency and the shorter wavelength. So this is larger frequency and shorter wavelength. Less energy down here corresponds to a longer wavelength and a lower frequency, or a smaller frequency. So practice just kind of thinking that out. Right? Draw yourself some little pictures. So you come to a question on an exam like this. Before you look at the question, draw yourself a little thing like this. Okay? Violet, ultraviolet. Ultraviolet gives me a sunburn. That's the high energy end. And then thinking about what the waves look like, we can figure out which is the high frequency and which is the long wavelength. So now we can just use this to order those colors. So in order of increasing wavelength, that means we want the one with the smallest wavelength first, and then middle, and then the longest wavelength. So this is the longer wavelength, and this is the shorter one. So what color is closest to the short end? So these are our three that we're looking at, red and green and blue. So blue is closer to the short end, so its wavelength is shorter. So we're going to list that one first. So blue, and then what's next? Green, and then red. Does that make sense? This is the short wavelength end, so blue is the shortest wavelength. We're supposed to go in order of increasing, start with short and go to long. Then they're asking us about frequency. Okay, Which side is low frequency, small frequency? Well, it's this other side, right? This is the small frequency. So of the three colors we have, red is the closest to that. So red is the smallest frequency, and then it's going to be green, and then it's going to be blue. Green is always going to be in the middle of these three. Energy per photon. Well, this side is high energy, right? More energy. So this side is less energy. Who has the least energy? Red. Go from smallest to biggest, because that's what the question wants. That make sense? So it can seem a little bit intimidating to like, ooh, we have to know the order of frequency and energy and wavelength and the colors and Roy G. Biv, UV light gives me a sunburn. Waves are higher in energy. Then you draw them and look at them. Well, short wavelength, big wavelength. Okay, any questions? I was hoping that was the end. Okay, 3 slides, we can do this. We can do it. So, going back to those ejected electrons. 1 photon of light at the threshold the threshold frequency, has just enough energy to dislodge an electron from that metal surface. And that's going to be equal to phi. That's the binding energy of the electron. So that's like the minimum amount of energy you have to put in to spit that electron out. If we shoot higher energy, higher frequency photons, the electron is going to get more energy than it needs to escape. So it's going to use some of it to escape, and then the rest of it becomes kinetic energy. So the kinetic energy would be the energy of the photon that it's been given minus the energy of binding, which is what it needs to escape. So this is my crazy mind. I look at this and I think about kids going to Disneyland. It's obvious connection, right? No? The binding energy here, that's how much you have to pay to get into Disneyland, right? The price of admission, which is like, what, $4,000 now? That's just crazy. Way too much, right? Well, let's just say it's $100. So it costs $100 just to get into Disneyland. And the energy of the photon, that is the amount of money that mom gave the kid. So if mom gives the kid $95, can the kid get in? No. Well, can't you let me in for 9/10 of the day? No. No, it's 100 or nothing, you don't get in, right? So if you don't have that minimum amount of energy, none of the electrons come out. If you have just the right amount, the kid can get into Disneyland, but they can't buy anything. They have no money left, right? What if mom gives them $200? So if mom gives them $200, they're going to spend $100 getting into Disneyland, and then they're going to have another $100 left to spend. And they could get maybe a cheeseburger. Does that make sense? So the electron needs a certain amount. It's called the binding energy. That's like the price of admission to Disneyland. If you get that much, the electron can leave. If you get more, the electron still leaves, but now it has extra, right? It's got some extra energy, and that's going to be its kinetic energy. If it doesn't get enough to leave, it can't go anywhere, and nothing happens. So that's what's going on with this graph here. Come on. This is the price of admission. This is the binding energy. So at a frequency of light that gives you that minimum energy, electrons will be ejected. If you go higher, they're still going to be ejected. What's different and does not show in this graph is now the electrons that are ejected are moving faster. They have more kinetic energy, but it's the same number of electrons. Come on. Okay, so suppose the metal will eject electrons from its surface when struck by yellow light. What will happen if it's struck by ultraviolet light? We need to know the relative energies of these lights, right? Roy G. Biv. What comes after violet? Ultraviolet. Forget which show was it that had Ultra Lord in it? I think it was Jimmy Neutron, maybe. His friend was obsessed with Ultra Lord. Anyway, so is UV light higher in energy than yellow or lower? Higher. Bless you. UV is higher energy than the yellow. So if I shine yellow light on this metal, electrons get ejected. So that must correspond to at least the binding energy or the price of admission to Disneyland. What's going to happen if I shoot higher energy at it? Are electrons going to be ejected? Sure. So it's not A. No electrons are going to be ejected. So we need to look at these other choices to see what the difference is. So here, electrons are ejected. Same kinetic energy as with the yellow light? More kinetic energy or less? More. It's going to have more kinetic energy. Choose a pen. Because they have more energy. They had enough to escape, but then they had extra, right? Not just enough. Any questions? I'm thinking it wouldn't be as fun though. I'm thinking of a different analogy where you've got a ransom to pay to escape from the metal, but I'll have to work on that one. So the idea here is sometimes light behaves like a wave, like in the box that the guy had on the beach, right? The light was behaving like a wave. Other times, it acts like a particle. The photoelectric effect. That has to do with particles of light hitting and ejecting electrons. Which behavior you observe depends on which experiment you're doing. We are observing the effects of what the electrons are doing, and so we're forcing, not the electrons, but the light, we're forcing it to behave like one or the other by observing it.